Okay, so just as a quick recap, when we talk about, graphing these polar equations, basically, we're still using the same concept of point plotting. So, you come up with your um, angles, anything from 0 to 2 pi. Since we know sometimes there can be repetition, you can go from 0 to pi, and then based on that, you come up with the R value. But then to get a better idea for our graphs, we can use symmetry. We can find the zeros where for what angle the R value is going to be 0, and for what value of theta will we get the maximum R value. So remember, with symmetry, we had talked about how we can check for symmetry using these tests over here. So you can have symmetry with respect to the vertical line, theta equals pi halves with the polar axis, which would be the horizontal axis, or the pole, which you can kind of think of it as the origin on your polar coordinate plane. We had also talked about a quick summary for for symmetry with the polar coordinates, and that was that if you have a function that has sine theta in it, so any numbers being multiplied into that, added, subtracted, doesn't matter. But if you're going to have sine theta in there, then we know all functions that have sine in them are going to have symmetry with respect to the vertical line, theta equals pi halves. If you have cosine as part of your function, then that will be symmetry with respect to the polar axis. So, this definitely makes it a little bit easier for us to identify what type of symmetry you might have. But it's always a good idea to check for all three types of symmetry, because as we had mentioned last time, you can have functions where you can have multiple types of symmetry as part of it. So just kind of keep that in mind. Now let's look into the other properties where you can have a maximum value or an R value. So I had picked an example here for us to work on. Let's look at number 20 here. So as you can see in the instructions, this one is asking us to find, this one is asking us to find the maximum and the zeros for the R value. And we are looking at number 20 over here. So our given equation is R equals 3 times sine of 2 theta, and we're trying to find the maximum and the zeros for the R value over here. So looking at our notes, so, the idea is we can use the table over here, create a table going from 0 to pi, and you can use it based on that. So let's go ahead and see what we can do for our given function over here. Okay, I thought it would let us. So we are going to do theta and then the R value. So you can start at 0. And remember, for this one, I was telling you guys that basically let the unit circle kind of guide you. So, if you're going for angles between 0 to pi, you can basically see what all of these angles would be. So you have pi over 6. Does this guy let us do symbols? There we go. So we can do pi over 6, pi over 4. What do we have? Pi 3s. Of course, you would have 2 pi halves over here. And, if needed to, you could, if you remember, in one of the examples we had seen, they had actually skipped the pi over 4 and they went with the other. So you can do that if you want, or for now, since we're just figuring this out, we'll go ahead and keep those. Then we get into 2 pi over 3, 3 pi over 4. Let's see, 5 pi over 6. And then our last one here should be pi. Okay, so once you figure your angles out, then you're going to figure out what your theta values are going to be. So remember, for this is where we get into, I was trying to see if I could make this table slightly bigger. I may have to do something like this. So to calculate these, then, of course, you will be doing each of the theta values into your equation. So 3 times sine of 2 times 0, what will that end up giving you? And then, that will be 2 times pi over 6, so on and so forth. So you can definitely put this into your calculator and just keep changing the pi values, or you can use, the only problem with that would be if you end up with decimal answers, right? Because, some of these where you have square root of 3 over 2 and those kind of numbers, then the calculator will only give you decimal answers. So that might be an issue I can see by just plugging everything into a calculator. So again, like I said, unit circle can be your friend. And since we're only working with the sine function, you are looking at the second coordinate of your unit circle. So all of these would be, our sine value over here. So when you are doing basically sine of 2 theta, and then we are multiplying that with 3 in the front. So as you can see, and here's angle 0. So for 0, of course, 2 times 0 will become 0. So sine of 0 is going to be 0. 3 multiplied by 0 will obviously also end up giving us a 0. So we know this answer is going to come out to be 0 over here. Now for your theta value of pi over 6. So you can see with pi over 6, we get 1/2. So that would be 3 times sine of, actually, since you have 2 times pi over 6, this will change, right? Because the 2 will go into itself once, go into 6 3 times, and this will become pi over 3. So this will be sine of pi over 3, and that's the angle you will need to use, which will be this number over here. So square root of 3 over 2, which will end up becoming 3 times square root of 3 over 2. So as you can see, this answer over here will be 3. That's the only problem I have with this one over here. Okay, looks like I don't have a square root symbol readily available. So let's do this by hand. 3 square root of 3 over 2 for that one. So, that's kind of the idea behind this. What will we end up with pi over 4? Because again, you will have to simplify pi over 4 being multiplied by 2. So as you can see, that will end up becoming pi halves. What will we end up for this value here? Three times sine of pi halves, what will that end up giving us?
3.
Yeah, very nice. So again, just to show you, your pi halves gives you a sine value of 1. So 3 times 1 will of course end up giving you 3. So since you have a denominator of 3 from the pi over 3, the 2 will not cancel out. So this will end up becoming sine of 2 pi over 3. So you can see for 2 pi over 3, your sine value again is going to be square root of 3 over 2. So same thing as what you got for pi over 6. This will also be 3 square root of 3 over 2. Okay, for 2 times pi half, what will we get? So the 2 and 2 will cancel each other out. Alrighty, so you are looking at sine of pi, and you can see sine of pi is going to be 0. So you end up multiplying 3 times 0, which of course ends up giving us 0. So we will have 0 over there. Now you are doing 2 times 2 pi over 3. What will that angle end up becoming when you multiply 2 times 2 pi over 3?
Four pi over 3.
Very nice, yeah, because again, the denominator is 3, so we cannot cancel out the 2, so you end up multiplying 2 times 2, which becomes 4 pi over 3. So that will be 3 times what number? So he will give us what? So you can 3, we are coming up with negative square root of 3 over 2. So now you will end up with negative 3 times square root of 3 over 2. For 3 pi over 4 as your theta value. What will this angle clean up into, guys, when you multiply 2 times 3 pi over 4?
Three pi over 2.
Very nice. All righty. So 3 pi over 2, you will see your sine value comes out to be negative 1. So this will be negative 3 over here. 5 pi over 6 as our angle. Again, what is that angle simplifying into?
5 pi over 3.
Very nice. So each of those denominators reduce basically by half. So let's see, 5 pi over 3. Again, your sine value is going to be negative square root of 3 over 2. So you can kind of see how every alternative number is coming out to be, you know, this answer with the square root of 3 over 2 with a positive or negative 3 in front of it. And then you're going from 0, 3, 0. -3. So let's see what we get for that last value here. And that's an angle of pi. And so you will see, in this case, you will end up with 2 times pi, which of course gives you 2 pi. So what will this answer come out to be? Sine of 2 pi multiplied by 3.
It would be 0, right?
Yeah, because you are back to the starting point, right? When 2 pi is right here where you have the 0. So sine value is going to be 0. So 3 times 0 will end up giving us 0. I guess we can type that in. Alrighty. So when we are talking about the maximum R value and the zeros, let's do that over here. And let me show you in your notes over here. So when we talk about the maximum R value, you will see we talk about that as an absolute value number. So that means you can actually look at where you have +3 and where you have -3. So always think about this in terms of an absolute value. So for us, the maximum value of R, okay. So absolute value of R. And that will be + or -3. So that means you are looking at this guy, and you know, of course, this will go in multiples, right? So we will say R equals 3 when theta equals, and actually let's write this as absolute value of R, because otherwise that could get confusing. So theta would be pi/4, 3 pi/4. And this will actually, you know, if we had gone all the way in our table to 2 pi, then these would be the other angles that would show up. So you can see they're basically multiples of pi/4 going from 0 to 2 pi. Okay, so that would be for the maximum value of R. Now for the zeros, of R, okay. So for this one, you can see we have 0, 0, and zeros over here. So that would be for, of course, angle 0, and then pi/2, pi. So can you tell me what the other angles after that should be? Zero, pi/2. So 0, pi/2, and pi. So what do you think the other angle would be?
3 pi/2.
Very nice. Yes, it would be 3 pi/2. Yeah, so Savannah, I was also thinking about 2 pi, but as it turns out, and I'll show you that here in just a second. Because we tend to keep our angles, trying to see where we had that mentioned. Your theta has to stay between -2 pi and 2 pi. I'm trying to see where we talked about that. So you're technically not including 2 pi in your calculation because, you know, again, the idea is 0 and 2 pi kind of fall on the same location, right? So you don't specifically have to actually include 2 pi. And either my eyes are playing a trick or I'm not seeing it. It may have been actually in the previous section for all I know. So yeah, technically 2 pi is correct, but since, like I said, 0 overlaps where the 2 pi already falls, we are actually not going to list out 2 pi. So these would be the angles going from 0 to 2 pi, where you would find your maximum value and your zeros. So this is kind of how I talk about, finding these values also. And, the other thing that helps us when you go through that table is you already have all the points now. So when you start graphing, if you were graphing by hand, then you've already got the points to help you out, and you would be able to, make your plots on the coordinate plane, and you would be able to come up with the shape of your graph. So that's the example for how to find our maximum values and our zeros for R. Now for the next example, let's actually look at, graphing one of these basic examples here. And again, they're talking about here, sketch the graph using symmetry, zeros, maximum values, and any other additional points. So we'll start with a basic example here, number 26, which is R equals 4 times cosine theta. Let's talk about symmetry first. So since this is a cosine function, what kind of symmetry will it have?
Polar axis.
Yeah,
Axis.
very nice, very good. And then again, remember, as I had just talked about, you can check for other type of symmetry with the line theta equals pi halves and the pole. But in this case, none of those other symmetries actually exist. So this would be the only symmetry that exists over here. Now, in the sense of saving time, your maximum R value will come out to be 4, because that's your, remember we had talked about amplitudes back in chapter 1. So you kind of think of 4 as that amplitude value, right? So since that is in front of the cosine function, that will be your maximum value over here. So that's why we're coming up with 4. Now, if you think about the cosine function, look at angle 0. At angle 0, your cosine value is +1. And we know that is the only time, because we just saw that with the sine function, wherever you had 1 or -1, we got +3 or -3 in the previous example. So in that same way with the cosine function, when you have +1 or -1, you are going to get your maximum, R value. So that's going to happen at angle 0. So in this case, your theta would have to be 0, because, again, when you would put 0 in here for cosine, you would get 1. 4 times 1 ends up giving you 4. So that's going to be your maximum value. And then for the 0 of R, your R value will be 0 when your theta is going to be 0. Okay, and when we graph this, so, this would be our polar axis with 0. This would be pi halves. Of course, we would have pi over here. And then 3 pi halves over here. So this will actually end up becoming Let's use a different color for our graph. Oh, we may have to- So this will actually end up looking, and we had seen something similar to this in our very first example, because this is where you end up getting, this is your pole, your zero. This would be R2 actually. Let's do it over here. So you would have 0 over here, 4 over here, you would be going out. And this is a really very basic, but that's kind of what, oh. Let's do this with annotation, that might work. Oh, okay. So origin, maximum value, and then, of course, we would do our table, and you would come up with a circle, which would end up looking like this. So that's kind of what this graph will end up looking like. Now, again, since you guys are not graphing by hand, I don't want to spend too much time on the graph itself, but basically that's kind of the idea of what your graph would look like. My recommendation to you guys, as I had mentioned on Monday also, is use some kind of support, so for sure that you have the correct graph. So you can go to your Desmos, this time go to a graphing calculator. Remember, I showed you that last time. Go under the graph settings over here, change this to a polar coordinate. And then here we would type in R equals 4 cosine theta, and you can see that's what your graph ends up looking like. And then, of course, if you needed to, you would be able to see, at the different angle values, what your points would end up looking like, if you had to do a little table and use that, to graph these functions, that kind of thing. So 4 cosine theta basically comes out to be a circle, which has a radius of 2, and it's going to be on the, the polar axis. But, of course, the main things would be the symmetry, the maximum value, and the 0 for the function. So any questions on this example over here, guys? Okay, sorry about that. My screen is acting a little funky. There we go. Alrighty. So this was with a circle. Let's see if we can do one of those other shapes that we had talked about, like a lemniscate, limacon. Oh, I think there was a rose petal in there. There we go. So some of these different shapes. So let's look at (32) over here. And you will see how the equation changes over here, right? So you will see now, instead of just doing 2 times sine theta, or even for that matter, -2 times sine theta, we're now doing 5 minus 2 times sine theta, right? So by adding that addition or subtraction, you are going to change the shape of your function. So let's take a look at this guy here. So again, let's talk about what kind of symmetry will this function have.
would it be the line of pi over 2?
Yeah, because this is a sine function, right? You can see it's got sine theta in there. So this is short for with respect to. Okay, so that will be our line of symmetry. Now, this is where you definitely want to kind of use this fraction of A divided by B and see which one of these, kind of shape are we going to have in our limacon over here. So you can see A is going to be the value which is in the front, and then B is going to be the number being multiplied with your function. So we are going to do A is going to be 5, B is going to be 2, and A divided by B will come out to be what?
$2.5.
Yeah, 5 halves, right? 2.5. And as you can see from our little chart over here, this is going to be A divided by B greater than a value of 2. So you are going to have this convex limacon. So you have the dimpled one if you are between 1 and 2, where you kind of see this little dimple happening here. But here, instead of the dimple, with the convex, it just kind of goes straight down. So it doesn't form a circle because, it kind of stops right over here and, changes the shape. So this is kind of what you are looking at for this guy. So this will be a convex limacon. Okay. So, again, for us to find the maximum values and the 0, we will obviously need to go back and work on this table over here. Ooh. Trying to see if I can copy paste that instead of having to, bring everything in. So again, I'm keeping those same angles from 0 to pi, and then we're going to use that with this function to see what our R value will come out to be. So in this case, you will see you just have sine theta. We're not multiplying the theta with any number, so you can directly go to the unit circle, get your values of sine theta, and then multiply that by 2, and then, whatever answer you get, we subtract 5 minus that value. So if we start at 0, well, of course, our sine value at 0 is going to be 0. So, this will come out to be 5 minus 2 times 0, which of course will give you 5 minus 0. So as you can see, that will come out to be 5 in this case. We still don't know if that's going to be the maximum value or not, because this is a slightly different function. So you would have to kind of work through this to see, where we get the maximum value. Now for the pi over 6, 5 minus 2 times. So for pi over 6, you can see your sine value comes out to be 1/2. So this would be 1/2 over here. So as you can see, the 2's will cancel each other out, leaving us behind with 5 minus 1, which of course then comes out to be 4. So that will be 4 over here. 5 minus 2 times your theta is now going to be pi over 4. So for pi over 4, you will see your sine value is square root of 2 over 2. So same thing here, the 2's will cancel out, but then this one will end up giving us 5 minus square root of 2. Now, as far as graphing goes, and if you were doing this by hand, You can convert that to a decimal, but for now, I am just going to leave this as 5 minus square root of 2. Okay, then let's see, r equals 5 minus 2 times for pi over 3. Pi over 3, you will see our sign value is square root of 3 over 2. So same thing's going to happen here. The 2's will cancel out, but then you are left behind with 5 minus square root of 3. So same thing here, 5 minus square root of 3. Okay, go ahead and tell me, what do you get for pi halves? The r value for pi halves. Alrighty, I'm seeing a couple answers come through. I've got Savannah, Andrew. So for pi halves, of course, you will see our sign value comes out to be 1. So that means you are doing 2 times 1, which will be 2. 5 minus 2 will end up giving you 3. All right, wonderful. Now let's see, for 2 pi over 3, I think we're going to be back into fractions. Yeah, you can see your sign is going to be square root of 3 over 2. So again, the 2's will cancel out, leaving us with the 5 minus square root of 3. And you know, guys, that's not a surprise, right? Because you do have symmetry with the sign function. So when you're on the either side of pi halves, you are going to end up with similar looking answers. And we even saw that in the previous example. Now, our next angle is 3 pi over 4. Same thing's going to happen here because 3 pi over 4 also gives you a sign value of square root of 2 over 2. So again, you're going to get the same answer, 5 minus square root of 2, as we did for pi over 4. So 5 minus square root of 2 over here. What will we end up with for 5 pi over 6?
Four.
Yeah, because you get 1/2. So again, the 2's cancel out. So I just realized as we've been working through this example for pi, you of course get 0. You would actually have to go all the way to 2 pi for this example. Will it let me? I was trying to see if it will let me add a couple extra boxes here at the end. Okay. So we know for multiples of pi over 4, so at 5 pi over 4, 4 pi over 3, you're still going to get similar answers to these 5 minus square root of 3, 5 minus square root of 2. They will change to positive, so it'll become 5 plus because your sign value becomes negative. But I actually wanted to show you where the maximum value is going to happen for this function over here, because we actually have not hit the maximum value yet. So let's look at where the maximum value will happen. So I'm actually going to include 3 pi halves, and then we can do 2 pi as the last one. Okay, there we go. So we're not overlapping. And then this guy should be 2 pi. Okay, so let's see, what do we get for pi over 4? 3 pi over 2. And at 3 pi over 2, your sign value is going to be -1. And that's actually where this changes. So you can see when I multiply -2 with -1, this actually ends up becoming +2. And here you will see we end up getting 7 as our value. And then what do you think will happen at 2 pi? What number will we fall back to when we get to 2 pi?
5.
Yeah, because you get 0, right? So same thing as what you had at 0, at pi. That's the same thing that's going to happen at, oops, 2 pi, and you will end up getting 0. So this is where you will see your maximum value right over here at 3 pi halves as your theta value. Oh, sorry, that should be a 5, not a 0. Okay, so, that's where you are going to be. And as you will notice over here, we didn't really hit any zeros on this table of ours. So that maximum value is all the information you're going to get. And as you can see in this table, we did, in this example, we did actually have to go all the way out to 2 pi, and we skipped some of the middle numbers, but you don't hit that maximum value if you just stay between 0 and pi. So now you've got the basic information over here. Now let's see what the graph for this guy will end up looking like. So R equals 5 minus 2. And this was sine theta. So you can see this is actually what the graph comes out to be. And right over here, you will see at the bottom, you hit your 7 right over here, because this is your angle, 3 pi halves, and this is where you come to 7. So if you only went between 0 and pi, then that's the only shape you are getting for your graph. So that's why for this graph, we need to go all the way from 0 to 2 pi so that we can get the entire shape of our graph. So that is what that guy ends up looking like. And as you can see, we have that convex shape, right? You don't have that little dimple in your limacon, because this is, your A divided by B came out to be a value greater than 2. So that's why you have that convex limacon. Questions on this example here, guys? Okay. Let's come back to our textbook over here. Okay, let's look at one of those rose petal type of examples. So for this one, we are looking at number 40. So this guy is R equals 3 times sine 3 theta. So as you can see, there's no plus or minus happening over here, right? Like we did with the Limacon example. This is not a straightforward 3 times sine theta because that is where you get those circles. So because you have the 3 theta plus the number in the front, this is what kind of hints at that this is going to be a little bit of a different graph, and you are going to have that rose petal shape to this. So let's take a look at this guy here. So with the rose petals, remember, this is what we had to see on how many petals we're going to have. So when your n is an odd number and the n value is what you have in front of that theta. So that's what you are looking at. So if the n value is odd, that's how many petals you will have. If the n value is even, multiply that number with 2. So our n value in this example is 3. So since n is 3, so our rose curve will have 3 petals as part of it. So let's talk about symmetry again here, guys. What kind of symmetry do you think this function will have?
It has symmetry about the line pi over 2.
Yeah, very good. Just like we saw with the previous example, because again, this is a sine function. So again, symmetry with respect to the angle theta equals pi halves. We already talked about this guy will have 3 petals. So this is a rose curve polar graph over here. Let's actually do the graph here first. So this guy will be r equals 3 times sine 3 theta. Okay, so you will see in this case, our maximum value comes out to be 3. And you will see that our value of 3 is coming out when our theta is, what's that, pi over 6, 5 pi over 6, and then at 3 pi over 2. You will see we get zeros. And actually, technically, you are getting zeros at different angles because, you know, every time a curve of this petal passes through the pole, you are coming up with a 0. So you are getting 0 at angle 0. And to me, it looks like at pi over 3 because this curve, you know, kind of coincides with the line pi over 3. You will see the same thing here with 2 pi over 3. This guy is coming here from pi. This curve is coming from 4 pi over 3, which makes sense because now you're looking at multiples of pi over 3. And then this angle over here seems to be coming from 5 pi over 3. So in this case, because, you know, with the rose petal, you keep overlapping, trying to make those 3 petals, you are going to get a lot of multiple places where you will see, you know, where that 0 value comes out to be. Additionally, each petal is also going to give you a maximum value because, you know, it has to go out that length that its maximum value is going to be. So if you have 3 petals, you will have 3 angles where you will get the maximum value. If you had like 5 petals, then you would have 5 angles, which would give you the maximum value. So the number of petals will actually also tell you how many angles you should have for the maximum value. And then, you know, of course, with the zeros, it becomes twice that number because each petal is going to cross the origin at, you know, twice because you have the beginning of the petal and the ending of the petal. So since you have 3 petals, you will see we had 6 angles where you have the zeros and 3 angles where you had the maximum value. Does that make sense? Yeah. So, again, obviously the way of finding your maximum and zeros, for this one, I would definitely recommend to create your table going from 0 to 2 pi to try and come up with all of these values. Okay, so I'm actually going to save this so you guys can have that as a reference. So this one, okay. I kind of wish I had saved my values here now. So let's see, that was pi over 6. Five pi over 6 and 3 pi halves. Yeah. And then for your zeros, the theta was 0, pi over 3, 2 pi over 3 pi. And then what did I have? 4 pi over 3 and 5 pi over 3. So those will be your zeros. So again, the reason why I'm not spending time doing the table, because I want you to be able to see different types of graphs. And, if we start calculating tables for each one of these, we will not get through all the different shapes. So we've looked at the circle, we've looked at the limacon, and now we've looked at one example for the rose curve. Any questions so far, guys? Okay. And let's do that one last shape that we had, which was the lemniscate. I think that's how you pronounce it. So, one of these infinity looking symbols, and you can see this is where your equation definitely looks a little bit different also, because you have the r square instead of just the r value, and then you will see even the a value is squared, and then you have your little 2 theta on the angle over there. So let's take a look at an example for this guy here. Let's get into our textbook, and I guess we'll do number 46. Oops. So r square equals 16 sine theta. Now you will notice in number 16, your theta does not have a 2 in front of it. Whereas if you look at number 45, where you have r square 9 cosine 2 theta. So it's not necessary that you have to have, a number being multiplied in front of the theta. As long as you can see the r square over here, and you can see this is a perfect square number for the a square value over here, you're looking at a lemniscate. So this one does not necessarily have to have a number being multiplied in front of theta. So just, something to note. So again, let's start out by talking about symmetry for this guy. And one thing we can do is, so that we kind of get an idea of what this graph will end up looking like, is you can actually take this equation and you can take a square root on both sides. So if we take a square root on both sides, you know, of course, square and square root will cancel out, leaving us with our value. We will, of course, have plus or minus because you are taking a square root. Now, since 16 is, you know, a perfect square, we can take square root of 16, which will come out to be 4, and then you will be left with the sign, which will be inside your square root symbol. So, you know, just to kind of get an idea of what would happen if we just tried to simplify this into R, because you still want to use, you know, the same idea of, I'm going to create a table, you know, take my angles from 0 to pi or 0 to 2 pi, you know, pick values for theta, plug it in to find my R values. So to solve the table, you will definitely need to, you know, clean up your equation and get rid of that R square and convert it into R. But as far as, you know, finding the symmetry, it's not going to matter if you leave it in the original form or if you take a square root. So what kind of symmetry this function has? And I'm just realizing that I picked like a lot of sine functions and not a lot of cosine functions, but that's okay.
Would be symmetric of about pi over 2, right?
Very good. Yeah. So sine function, you will automatically have, yeah, Andrew, very nice. Theta equals pi over 2. Now, let's take a look at what this graph will end up looking like. And this one, we will have to play around a little because I have not tried this in Desmos. So if we just did R, does it let us use, or am I going to have to type this separately? We might have to figure this one out. So we know it comes out to be R equals plus or minus 4, and then square root of sine theta. And we will put this from pi. Okay, if this is with the positive 4, what happens when we make that negative? Okay, yeah, so we will have to do this. So let's copy, paste, and change that to negative. And I guess it will not let me change the color, but basically both of these together make your graph. And let's see if we can zoom out a little. So as you can see over here with this graph, you have a maximum value of 4, which will happen at pi halves and 3 pi halves. And then you will see we are definitely coming to zeros from here, you know, at angle 0. And then from here at pi, and then same thing here from pi, from here, and possibly 0 or 2 pi from there. So that's kind of what this guy will end up looking like. The other symmetry that we didn't really check for, but you do see that, you know, of course we see the symmetry with the line pi halves, but this guy actually also has symmetry with the pole, because if you were to take the distance from the pole, and let's say we'll use this line over here. So if you pick this point, then this distance from the pole is actually going to be the same if you pick the point on the opposite side of it. So this distance would then end up becoming the same. And this is going to be true throughout your, you know, shape of the graph, throughout the lemniscate. So, you know, if you picked this point over here, then that means you're looking at this distance from the pole. That would be the same if you picked this point over here and you look at this distance. It's going to be same. So this one actually, even though we didn't check for it, will have symmetry with respect to theta equals pi halves and it also has symmetry with respect to the pole. And you can see that better in the graph. And again, you can use those tests that we talked about at the very beginning of 6.8 to try and check and see if this will have symmetry with the pole. And you will definitely see that that's going to work out. So this guy will be a, did I spell that wrong already? Lemniscate. That's what your graph will end up looking like for this. So we had maximum value of R. And so you can see again, taking that square root will definitely be beneficial because, otherwise you may be tempted to say, oh, maybe the maximum value will come at 16 because that's what that A value is there. But remember, that's not the A value. This is technically a square that you have over here. So your A value is actually 4 and not 16. So that's why your maximum value comes out to be 4. And then those two angles were pi halves and 3 pi halves. And we can kind of zoom out a little. And you can see that's where those angles coincide with this guy. And then your zeros, of course, are at 0 and pi. And again, you will notice these if you were to complete a table for these guys. You would definitely be able to get those values from the table. Questions on this example here, folks? Okay, so practice a little bit with the Desmos calculator. If you are not familiar with the polar coordinates, just make sure you change that setting so you can get the polar coordinate, and that will help you identify your graph, because I think that will make your life a lot easier in 6.8, when they ask you to choose the right graph. And if they specifically ask you for what the symmetry is, what the maximum value and zeros are, then you want to do the table. But if they are just asking you to sketch the graph, then use technology to help you find the right graph. So that's pretty much the last part that we had to talk about, because I did go over the handout and the different examples with you. And you can see there are, example here with even petals. So this one had an n value of 2. So 2 times 2 will end up giving you 4 petals. So you can kind of see what that ends up looking like. Here's an example for a lemniscate. So this one actually only has symmetry with respect to the pole. This is not symmetric with the line pi over 2. Even though this is a sine function, you will see it does not give you that symmetry with the pi halves as we would expect. So, some of these examples can kind of surprise you a little bit. And then, as I was telling you last time, keep this little, chart here accessible, so that way you are able to figure out, if it's a lemniscate, what type of lemniscate is it going to be, circle, rose petal, or these limacons. And, of course, you can see there's 4 different types of graphs you can get with a limacon also. So this kind of wraps up, all the material that we needed to talk about as far as chapter 6 goes. Again, you have your practice final exam in WebAssign. So once you finish your homework, try and spend some time with it. I did want to show you something actually. Let me get into WebAssign here. Okay. And this is in teacher mode, so that's why the screen will look a little bit different. So I'll show you how I've designed this practice final exam. So you can see I've tried to give you every single type of question that you can possibly see in your final exam. So, this one here, the reason it has so many questions is because even if it's the same type of question, you will get to see multiple different, options for it. So let me kind of expand this out a little bit. Okay, so you can see we have our, starting right from chapter 1, section 1, you've got your coterminal angles, complement and supplement. But look at this, you have your complement and supplement over here, and another question with complement and supplement. So the idea is, these ones here are definitely in radians because you can see that's pi over 3, pi over 4. Now, when you look at something like this, they're numbers, but remember, again, we had talked about the distinction. If you don't see the degree symbol, don't assume it's degree. So that's the same thing happening here. You have 3 and 0.5, but these are still in radians. So that's why I've included both types of examples in the practice final, because any one of these can show up on the final exam. And you will see that with a lot of different examples over here, multiple different application problems. Trying to see if I can show you another one where the repetition happens. Okay, so right over here, both of these questions are asking you to use a calculator to evaluate the trigonometric function. So again, one of them is giving you tangent of 2 pi over 9, but the other one says secant of 2.4, right? So again, just to make sure you guys are understanding that when you don't see the degree symbol, don't assume that the angle is in degrees. Again, these are both examples of radian. So a lot of these examples will have these multiple questions because any one of those can show up on your final exam. So that's the reason why your practice final exam has 102 questions, because I'm trying to give you every single type of question that you can see. So you can see even here from 6.8, you've got your Lemnis gate over here. So this is r squared 16 sine theta. This one is r squared 25 cosine 2 theta. So again, you're seeing multiple examples of the same thing. This one was a rose curve example here. This one also is a rose curve example here. So you will see multiple questions for the same type of question in the practice. And that's only because I want you to be aware any one of these can show up in the final exam. Now, the final exam does not have, obviously 102 questions because we'll be here forever taking the final exam. So don't get scared when you see the practice with that many, because that's the idea of practice, right? You should be able to see all the different versions of the same problem. So that way you are, let's see, you are allowed to use notes on the final exam. So you can use notes, formulas, cheat sheet, whatever you think you will need that day. You can use Desmos calculators. If you have a handheld calculator, you can use those. All I say is make sure the work is your own and not somebody else's work. So, make sure you are working the problem, make sure you are the one coming up with the answer and not, I'm not even sure what the other thing might end up looking like. Do not use your cell phones as a calculator. Either have a traditional calculator as you do, or like I said, Desmos is definitely good. And you can have both the scientific and the graphing calculator open, just open them in a new tab, each one of those. So that way you can go back and forth depending on which calculation you are doing. But yes, notes are allowed, formulas, cheat sheet, whatever you need. I will see, I may actually have a cheat sheet I may have created, when we were still doing on-campus face-to-face classes. So I will share that with you. And if you want to add anything else to that, you can do that as well. So that may be a good starting point. So you're not having to go and find everything from each chapter. So I think I may have a cheat sheet already designed for the final exam, and I'll post that in D2L so you guys can have access to that, download it, save it on your computer. Any other questions coming to mind about the final, guys? So I will give you extra time on the final exam because again, I don't want you to feel rushed. So you should have, I believe, 2 hours total, even though it's an hour-long exam. I do give you 2 hours, just like we did for our other chapter exam. So that way you can take your time, you don't feel rushed, and hopefully do your best on the exam without feeling the pressure of it, which I know you will feel a little bit of the pressure. That's just normally how everybody works. But I'm really hoping with all the hard work you have done for the semester that you will already know what your exams feel like, what my exams are like. So that nervousness of the final exam hopefully is not going to be too bad. I do want to let you know that I am having a small procedure done on Friday, so I'm actually not going to have access to the internet on Friday, and maybe part of Saturday. It just depends on how long the recovery takes. So if for any reason you do have any questions and stuff, if you can get to me between today or tomorrow, that would be better. But if you do send me an email on Friday, I will try to get to it as soon as I get back home. I have access to the internet, and I will definitely try to keep up with my emails on the weekend if I can. But it may end up becoming Saturday evening or Sunday, and I know our assignments are due Sunday at midnight, so that's why I kind of wanted to give you guys a heads up so you don't panic if you don't hear from me on Friday or Saturday morning. Yeah, but anything, especially with chapter 6, if you have any questions, try and get to me earlier if you can, so that way I have enough time to reply back to you. And you can get chapter 6 out of the way, and then you can spend the rest of the time finishing any of the older homeworks and quizzes if you wanted to, or studying for the final. So we'll be meeting on Monday at our regular time at 4:15 for the final exam. All right, guys, if you have any questions, I'll be happy to answer them. And if not, good luck, everyone. Study hard. You guys have done amazing this semester, and don't be afraid of the final exam. You will do great. So I will see you on Monday afternoon, guys. Have a wonderful weekend. Take care, everyone. Stay safe.
Thank you so much. Good luck with your
You-
procedure.
Thank you. Oh, thank you.
See?
Bye. Hey, Alicia.
Hi.